Hello, Computer Science 221 students. Can you hear me? Good. Hello. Okay. Hopefully you had a good long weekend. Today we're going to cover week 3-1. It's called Direct Proof and Disproof Part 1. Now that we know some logic and now that we know some quantified statements, we can combine De Morgan's laws, we can combine some argument forms and negations and stuff, and change to more formal statement. And with that formal statement, we can prove some mathematical statements. The first thing that we're gonna do is actually discuss about our upcoming events as well as practice midterm. Um, yeah, and then the videos. Yes. So the first thing I want to talk about is uh, look. Okay, I'm gonna answer Ryan's question first. Are the Tuesday live lectures in place of some of the videos now? Also doing the okay. Um, this is one of the reason why I'm going to edit this video after the class and post this video as the first thing for on in media gallery for week 3. You guys know week 3 notes and assignment. What happened? Do we have them or are they canceled? That's correct. Week 3 notes, week 3 assignment will be canceled. Uh, I think Ryan's question is speaking of the future notes and future assignment. For week 4, Tuesday, we're going to have a midterm. So in a way, I'm going to make the prerequisite video for week 4-1, week 4-2, week 4-3. So those are 4 marks, right? But week 5, Tuesday, I'm going to do like this. And week 5, Tuesday's notes, I'm going to provide you slides as usual. Well, not usual, actually. This is my first week doing this. And week 5-1, week 4-1 will be for marks. So everyone, why don't you come join me on Tuesday and just print out the slides in advance and just write the stuff on your paper while we proceed with the Tuesday's lecture. Did I answer your question, Ryan? Okay. So that's the plan for the first video of the week. And next thing that we can do, I want to talk about is this. If you go to Canvas modules, I'm going to post the solution to the practice midterm on May 28th, which is Friday. And as usual, there are blank live class for Fridays slides with the solutions. And then I posted 3-1. Oh, well, actually, I think I sent this PDF slides last week to you guys on Friday. So you guys have them. Week 3-2 is also available. And for week 3, I'm going to post the problem sets because you don't have to hand in anything for week 3. I'm going to just give you make a problem set containing week 3-1 related questions, week 3-2 related questions, and week 3-3 related questions as a single file. And I'm going to type everything and post it as soon as it's available. Personally, for me, everything is cramped in, so it's a little bit busy for me. But however, it should be done. Okay, it should be done. Don't worry. I'm not gonna post this like on Monday, right before the midterm. So it should be done today. And week 3 assignment will be canceled due to midterm. And another thing that I want to talk about is practice midterm. If you guys click quizzes on Canvas, you guys will see nothing at the moment because it's not published. The reason is I want to select the good questions for you guys for the midterm to prepare you for the midterm. And I'm still, when I finish some work, I always think twice, 3 times if this is good for you guys or not. And I think these questions that I created yesterday are not 100% making me happy because questions maybe maybe I don't know. I want to take a look at what I want to take a look at these questions one more time and post it today for sure. Is it okay? Could you guys wait until few hours later after the lecture? Yeah, some of these questions might be familiar to you from week 1 assignment. And some of the questions are not familiar to you because it's week 3-1 or 3-2 here and week 3-1 here. So although I set 7 to 9 written questions on the midterm, I might put 10 or a little bit more than 10 because it's practice. More practice, the better. Do you agree? So more practice, the better. So for the practice midterm, I might put more than 9 questions. Please don't be surprised. Right, okay. All right, so as soon as it's available, you will see under quizzes on Canvas. Okay, that's about practice midterm. And yeah, I think we are ready to go. Our goal for today is to cover this slide together. Any questions before we begin about anything coming up, events? If everything is clear, then we can start the lecture about direct proof and disproof part number 1. Okay, we're gonna start from very, very simple stuff. As a review of symbols, by now, I hope you guys remember the board face Q represents the set of rational numbers, the board face Z represents the set of integers, and the board face Z plus represents the set of positive integers. And it's discrete structure course. We love these structure, positive integers. It's counting 1, 2, 3, and so on. You guys know what sequences are. We usually represent sequences A1, A2, A3, and so on. Do you agree? So we always count things 1, 2, 3, and so on. Okay, and I think I received a question. Daria question is no assignment next week. Okay, I'm gonna make it clear, no assignment due next week. No assignment due next week. Because we have a midterm on Tuesday, right, everyone? However, new assignment for week 4 will be published next week so that it's due in week 5. Does that make sense, Daria? Okay. All right. Okay, and I think Daria emailed me about very nice idea about project implementing what I talked about last time. It's kind of same thing, like login system, but you can do your own example, as well as encryption system. So speaking of project, I will be providing you more information about the project during week 4, okay? Sometime after the midterm. And it should, I want to make this project not too huge because you guys still have to do the homework, right? Week 4, week 5, and week 6. And then during the week 6, you might also have to do preparation for the final exam. And Daria has a question. Can we proof check with you before submitting? Yes, of course, yes. Of course, I cannot say correct or incorrect like clearly. No, yeah. You can check with me, okay? You can during my office hours. Yeah. By the way, UBC has posted our final exam date and time. Did you guys notice that? Anyone knows? Okay. Um, UBC announced that our final exam schedule is on June 24th, I believe, at 9 a.m. I could be wrong. Um, in case I could be wrong, everyone, uh, you're allowed to check this by going into UBC, your Student Service Center, UBC SSC, and under exam schedule, you will be able to find when and what time we're going to have the final. I'm actually, thank you, Kira. Thank you. I'm actually quite happy that we have June 24th instead of June 21st. It's going, we have some time before the final. Okay. All right, everyone, we're gonna use the symbol Q, Z, and Z plus a lot today and this week, including the midterm. Diarrhea has a question. Will it be 3 hours? What does UBC SSC says? Is it 9 a.m. towards 12 p.m.? Only 9? Okay. Unless they say something, because last term, I got an email from very executive level at UBC that it has to be 2.5 hours last term. Do you guys remember? Term 2. But ever since I started working at UBC, it always has been 3 hours. So here's my plan. Unless they tell me to change to 2.5 hours, I'll be sticking with the usual convention hours, 3 hours. Sounds good? So it's either 2.5 hours or 3 hours. So it's like this, everyone. 2.5 hours or 3 hours. If UBC denies 3 hours, therefore, what is the conclusion, everyone? That's right, 2.5 hours. By what kind of argument form? By elimination. So if UBC eliminates the possibility of having 3 hours exam, then we're gonna have 2.5 hours, that being true. Okay. So too much talk of what we've done in the past. Okay, everyone. Are you guys ready to do some simple proofs today? In order to do some rigorous proof, we need to know how to represent the number in general. For example, look at this pattern: plus minus 2, plus minus 4, plus minus 6. Did you notice that these numbers is the same as 2 times by 1? This number 4 is the same as 2 times by 2, and this number is 2 times by 3. So everyone, dot dot dot, as it goes along, what is the general expression of an even number? The general expression of even number looks like this. It has a DNA, looks like 2 times by some integer. Do you agree? 2 times by some integer. So can we just represent the general expression of even number to be 2 times by some integer k? Here, let's call it k is just some not random, but some integer. Okay. Now, look at the pattern here. For the odd integer, 1, 2 times by 0 plus 1. Do you agree? For the first term. And then second term is 2 times by 1 plus 1. And then the third term is 2 times by 2 plus 1, and so on. So can anyone tell me the general expression of an odd integer? As it goes along, the general expression of odd integer looks like 2 times by k plus 1. Yes, thank you, Ryan. 2 times by k plus 1. And you guys know k is some integer. We're going to use this expression in 3-1 video and 2k plus 1 video. Sorry, not 2k, 3-2 video that will be coming up right after I post this video. Okay. All right. Let's move on, everyone. Now, this informal statement here, even integers represented as 2k, all the integers represented 2k plus 1, we can change these expressions, these statements, into a formal quantified statements. Like, you see, we say some integer k. Whenever you hear the word sum, it's either universal or existential statement. But whenever you hear the word sum, which one is correct? Should we use for all or should we use existence statement? Whenever we hear the word k is some integer or k is an integer, well, actually, I have to be a little bit careful. K is some integer. So whenever we hear the word sum, then we have to use existential, yes. So let's write even integers definition, all the integer definitions formally. Okay, let it begin. We say n is even if we can find special k integer. There exists k in Z such that n is equal to 2 times by k. If we can find our special integer k such that if we can represent n to be 2 times by that k, then n must be an integer. Similar to the n is odd case, there exists k in Z such that n is equal to 2k plus 1. Okay, so that's the answer for definition of n is even, n is odd. So let me put a big box around this here, because we're going to use this a lot. Okay, and these problems are kind of easy, probably easy for everyone here. Is 0 even? Of course, yes. Because we can represent the 0 in terms of 2 times by some integer. Can we just call the some integer to be 0? 2 times by 0 is 0. That's why it's even. How about part B? You guys all know that negative 301 is odd. So it's yes. Because we can represent negative 301 to be 2 times by some integer. What is that special number here, everyone? 2 times by what gives us negative 301? It should be negative 151, right? Negative 151 plus 1. Sorry, my question is supposed to be, which integer should we multiply with the 2 plus 2 and then plus 1 so that we get negative 301? That was my intention. And here, negative 302 plus 1 gives us negative 301. That's why it's odd. How about part C? Do you think 6 times a squared b is even? Yes or no? What do you think? Six times a squared b. We don't know what a or b are, and we don't care. We don't care whether we have to know a and b specific numbers. Stick with the plan, everyone. The plan is, as long as you can represent a number 2 times by something, 2 times by some integer, then you can call that number to be even. Do you guys agree? You can call that number to be even. So here, look at this. 6 times a squared b. It can be rewritten as, everyone, 2 times by bracket. What is the leftover here? The leftover is 3 times a squared b. Do you agree? 3 times a squared b, like this. Since 2 times by some integer is an even, we can conclude that this is yes. 6 times a squared b is an even integer. Okay. How about this? 10 times a plus 8b plus 1. Do you think this is even or odd? What do you think? We have plus 1 at the end, and we have multiple of 2 for 10a, multiple of 2 for ab. So if I represent this number 10a plus 8b plus 1 using a bracket, for example, it's better, right? It's equivalent to, what is the common factor? 8 and 10. The common factor is 2, right? So if I take out 2 bracket something plus 1, and that something is 5a plus 4b, surely 2 times by some integer plus 1 is an odd integer. Do you guys agree? So it's actually yes. Are you guys following me so far? Because knowing how to change this form, it's going to be very important today. Okay. Okay, thank you. So if you understood the definition of even and odd, let's move on and do some discussion of prime numbers and composite numbers. You know, our goal today is to do with even odd integers as well as prime and composite numbers. So as a warm up, everyone, you guys by now know that the importance of prime numbers. And I talked about Riemann hypothesis. Anyone actually researched about Riemann hypothesis after the Friday's class? Anyone? Riemann hypothesis, I made one mistake on Friday's lecture that it should be $1 million prize, not 10 million. Sorry, I was hoping. I was speaking my wish, but then it was $1 million. Even if it's my wish, I don't think I can get the $10 million. So, or $1 million. So if you guys solve the Riemann hypothesis, please don't forget me. Okay. All right, everyone. Okay, good. As a warm up, everyone, prime numbers are, what is the most smallest prime number? The smallest prime number is, the smallest prime number is 2. Do you agree? 2. And that's the only even prime number. And everything else is odd, like 3, 5, 7, 11, and 13, and so on. The numbers that are not primes are composite. Oh, by the way, everyone, that's a good question from Surajbil. When we talk about primes composite, let's consider positive integers. Positive integers, okay, listen carefully. Positive integers with this inequality greater than 1. Could you remember? Greater than 1. Okay. And it's due to unique factorization domain, unique prime factorization, because in week 3-2, I've made a video about that. So after this video, you can watch week 3-2 about unique prime factorization. You know what? We cannot assume prime to be we cannot assume prime number to be 1, because okay, I'm gonna talk briefly. Okay, in case you guys are wondering about it, and it's live, what's the advantage of having a live session? You guys ask me question, and I give you one example to answer. For example, Do you agree 72 can be written as 2 times 2 times 2 times 3 times 3, right? And 72 is equal to, sometimes some people write 2 times 2 times 2 times 3 times 3 as a prime factor. Or sometimes people write down 3 times 2 times 2 times 2 times 3. But everyone, tell me, the first factorization and second factorization, are they different or technically the same? Different or same? It's the same. It's unique, right? Unique factorization. So we want to represent each number, each positive number as a prime factorization. However, if we consider 1 as a prime number, then this uniqueness will break. And more detailed information about this will be discussed on Friday. How about this? On Friday, when I really talk about unique prime factorization on Friday. Okay, and this video will be uploaded as soon as I upload this. Okay, cool. Composite numbers are integers more than 1, like greater than 1, such that not primes. For example, 4 is a composite number. And then what else? 6 is a composite number. 8 and 9 and so on. These numbers are composite numbers, right? Okay. And I need to make some space, everyone, because I'm about to tell you one of the important property of prime numbers. Okay, take a look, everyone. For example, 3. What is the definition of prime number? Definition of prime number is the only factors of 3, for example, here are 1 and itself. For example, 3 is equal to 1 times by 3. Or if it can be written as 3 times by 1, and if these are the only factors of 3, then surely 3 is a prime number. Do you agree? And what do I mean by composite number? The composite number is at least one pair of factors, like 2, 6 can be written as 2 times by 3. If you can find at least one pair of factors of 6 where each factor is more than 1, see, 2 is more than 1. 2 is more than 1, less than the final number 6. And then 3 is more than 1, less than 6. If you can find out at least one pair of numbers such that their product becomes 6, then we can call these numbers as a composite number. So here's the important statement here. We say n equal to r times by s if we can represent the number n equal to r times by s, and the only factors of n are either 1n or n1, then we can say n is a prime number. So like this, if 1 times by n or n times by 1, if the factors of n are, the only factors of n are 1n and 1, then we can say n is a prime number. Otherwise, if r and s is more than 1, less than n, then we say composite, the number is a composite number. Okay? If you're confused, please feel free to ask me questions, because I'm about to write down the quantified formal statement of prime. Okay? We say n is a prime number. Of course, n must be more than 1. You guys know that. For all r s in positive set, like positive integer set, if you can represent the number n to be the product of r and s, say r times by s, then, right, then we have only two cases. Either r is equal to 1, s is equal to n, or r equal to n, s is equal to 1. Do you understand? Only one of those two cases for n to be prime. then either we have two cases, R equal to 1 and S equal to N, or another case is R equal to N and S equal to 1. So one way or the other. If you have other case, then you have to consider it as a composite number. So the definition of composite number is if you can find at least one pair, if you can find one pair of the numbers that is more than 1 less than n, then surely this number 6 is a composite number, right? Whenever I say 1, then it's a good indication of using existential statement. There exist a pair of numbers Rs in the set of positive integers like this, such that if you can represent n to be the product of R and S like this, Rs, and if you have condition where R and S to be this one, more than 1, less than n, like R is this, greater than 1, less than n, and S is greater than 1, less than n, then we can say n is composite. Do you guys agree? So here's the definition of primes and composite. I'm going to use this definition of prime and composite at the end of part 1 lesson today. Okay, so stay tuned. Please, I'm gonna say one more time when it's needed. Okay, otherwise, let's enjoy some more relaxed question. It's more easier question here, which is this. Proving existential statement. You guys know when we prove like this statement, there exists X in D such that the predicate Q of X. When we want to prove existential statement, do I need to prove every element in the domain that makes the function Q of X to be true? Or do I have to find only one example where this predicate is true? The first one or second one? Perhaps my question wasn't clear. When we prove an existential statement, do I need to prove every single X in the domain that returns true? Or do I have to find only one case, one situation where if I put the X into the function and returns true? Thank you, everyone. The answer is 1. You only have to find one case. So we just need only one case that makes the statement true. Okay, let's see how this problem of this turns out. Prove that there is an even integer, there exists an even integer n that can be written as a sum of 2 primes. So sum of 2 primes. There are so many answers, everyone. We just need to find one case that makes the statement true. Anyone has answer to this? There's so many choices where an even integer can be written as the sum of the 2 prime numbers. The answer that I can think of that comes into my mind right now is 10. You guys all agree that 10 is an even integer, and it can be written as the sum of the 2 prime numbers, 3 and 7. Even. And then you guys know that 3 is a prime and 7 is a prime. So there you go. This is the proof of the existential statement. Right, Daria, thank you. 7 plus 3, 7 plus 5, and so on. There's so many choices. Okay, this is how you prove existential statement. Proving existential statement is the same as disproving a universal statement. For example, look, you guys know that universal statement looks like for all x in D. Oh, actually, someone had a question. I am fair. So we just have to give an example to prove in this case. Sure, I am fair. This is the proof. Of course, it's not a. There's no proof by example, but uh, for this kind of existential proof, only one example is good to go because it proves the statement. However, I think your question is much better if I talk about universal disproving statement. Sometimes for all x in D, if blah blah blah, then blah blah blah. This kind of universal conditional statement might be false. It could be false. If the original universal statement is false, everyone, what is the negation? What is the truth value of the negation? If this is false, the negation is what? If the universal statement is false, then its negation should be true because it's a statement. It's either true or false, right? So the negation, which means, let me write it for you. There exists x in D. There exists x in D such that, oh, I'm gonna be pretty happy. I don't know if I asked this question in the past or not. What will be the rest of the sentence? It might be, fill in the blank on the midterm maybe. For all x in D, if P of x then Q of x, there exists x in D such that what is the negation of this conditional statement? P of x and not Q of x. Thank you, I am fan, Kira and Carol. Good job. So P of x and I'm gonna just put n to be English and not Q of x. Okay, you guys know from before P implies Q is logically equivalent to not P or Q, right? So if you use De Morgan's law on not P or Q, you will end up having P and not Q. Okay, good job. Okay, well done, everyone. So we have this kind of negated statement. We just have to prove that this must be true. Wait a minute. Disproving a universal statement is nothing more than proving an existential statement, just like this before. Proving an existential statement just requires one example. So there you go. Disprove this universal statement by finding a counterexample means just one example that makes the statement false, or one example that makes the negation true. Let me quickly write down the negation of this universal statement. The negation is there exists A, B in R such that, I'm gonna write it, such that, okay, and then you guys mentioned that A squared equal to B squared is P, right? So we just have to copy and paste this, A squared equal to B squared. But A cannot be equal to B. A cannot be equal to B. So our goal is to, make this negation statement true by finding one example. Anyone has a good example where we satisfy this hypothesis, A squared equal to B squared, but A cannot be equal to B? There are actually more than one example. Okay, Nathan has chosen 2 to be A and -2 to be B. So there you go. I'm gonna write down I'm gonna choose Nathan's question or suggestion. A is equal to 2, B equal to -2, right? Surely, if you square the left-hand side, like A square, B square, you're gonna get the same number. So clearly, A square is equal to B square because 4 and 4, because we have 2 square equal to -2 square. But however, here's my big but. 2, which means A, cannot be equal to -2. So 2 does not equal to -2. So therefore, so what is the answer, everyone? Therefore, the original statement is false. The original statement is false. And we've proved that using one example, counterexample. Okay, so that's about finding or disproving a universal statement. Okay, so far, everyone, how do you feel about disproving universal statement? So far, good? Right. Disproving universal statement requires only one example to disprove. Have you guys ever thought about proving universal statement? Proving universal statement can be a headache, like Riemann hypothesis. You want to prove all solutions living in the critical line. Okay, so here's the question. If you guys now comfortable disproving universal statement, how about proving universal statements? Proving universal statements can be very headache one. And universal statements looks like this. For all x in D, okay, if P, then Q, it looks like this. Sometimes people being clever, you can combine the hypothesis P of x inside of the domain to make it true set, and you just write down Q of x. So that's more shorter form. But we are more familiar with the if-then statement, so I'm gonna keep it as it is. Okay, so proving universal statement usually tend to be more harder than proving existential statement. So here's one point. More difficult than proving an existential statement. Okay. Now, however, proving universal statements is not the end of our life. It's not the end of the world, because sometimes, depending on the domain, proving universal statements can be easy. For example, if you have two cases, or two or three similar, but two cases, two different ways to prove a universal statement. Okay, so for example, let me make some space. Okay, and I kept talking about the domain, and in like right here, D domain. In computer world, usually when you code it out, element, you check every element in the domain. If you insert this to the predicate, what happens? If you insert the other number into the predicate, what happens? So that's what the computers do, right? In other words, our domain is finite. In other words, the array contains finite number of element. If we have finite number of element, life might be easy unless this element is not too large, unless the number of elements is not too large. So suppose we have a small amount of elements in a domain. So finite domain. Then for me, as a picture, I'm going to use 3 elements, x1, x2, x3. I only have 3 elements in the domain. In this kind of finite domain, you have some special method, just plug in number, and see how the function returns. Versus the opposite of the finite domain, it's infinite domain. Infinite. Or even though it's finite, the number of elements could be large, right? So infinite domain looks like this. As a set, we have x1, x2, x3, and continue forever. Like there's so many elements in the infinite domain. Okay. I have a special name for this finite domain proof for universal statement. According to the textbook, they say when you're working with a finite domain, it says method of exhaustion. Method of exhaustion. Okay. Did I pronounce it okay? Exhaustion. It's I practiced a lot last night. Exhaustion. Okay. Too many zuz, and it's hard here for me. Exhaustion. Okay. Now, infinite domain has a special name. I'm not gonna use the textbook name for this. It's too long. I'm gonna first write down what textbook says. The method for this infinite domain is called method of generalizing from generic particular. Isn't it too long, everyone? This method of generalizing from generic particular, we don't want to say this all the time. So I made a new name for this. Just call it method of selecting arbitrary element. Arbitrary element. So it's like this. Because we cannot check every single elements in the domain, you just pick a random number, number that has a same DNA as other elements, and if with that DNA you do some proof. If you do that proof for that particular element, it proves the truthness of all the other elements as well, because that particular randomly selected generic element has the same DNA as others. So if we can prove that element truthness, then it implies just the truthness of the other ones. Do you understand so far? For this infinite case? So for the infinite case, I'm going to practice how to do this, okay, using an example. For the finite domain, also I have one example, and it's coming up right now. The question is, use the method of exhaustion to prove the statement for all n is z if n is even, and this, we have two hypotheses, then our conclusion is that n can be written as a sum of two primes. We did similar problem before. You guys gave me, or I gave you 10 equals 3 plus 7. And I think Daria, if I'm not wrong, Daria gave me example 12, 14 and so on, right? So we're going to use that kind of idea for this proof using method of exhaustion. Okay, everyone, let me just write down the domain for you. Okay, domain here, and you guys tell me which element belong to the domain in this case, or even truth set you want to call it. Okay, so I'll wait for you guys. Read this carefully. We have n is even and n must be in between 4 and 8. So how many numbers or which numbers should I put it in as a domain? Kira said 468, and I totally agree with her. So in the domain, it should be 4, 6, 8. So how many times should you check for truthness? Only 3 times. So that's why method of exhaustion is simple when you're working with a finite domain. So here's the proof. How many cases? 3 cases, right? Case 1. Case 1 is when we consider n to be 4. So case 1, suppose n is equal to 4, then we can write 4 as a combination of, in other words, the sum of 2 prime numbers, say 2 plus 2. So case 1 is proved. And similarly, case 2, suppose n is equal to 6. We can write 6 in terms of 2 primes, say 3 plus 3. Okay. And case 3, suppose this time we chose n to be 8, which is the last number in the domain. We can write 8 is equal to what plus what? 3 plus 5? 3 plus 5? Okay. So second case is true. Third case is true. So we have all the elements in the domain became returned true with the function here. Therefore, we've proved the statement. So therefore, the statement is true. Okay. So everyone, this is one way. This is one way to prove universal statement. The next question is, what if our domain looks ugly? Like we have infinitely many elements in the domain. So here's the question. How do we deal with a statement? How do we deal with a statement with infinite number of cases? The answer is, what was the special name that I gave you when you're dealing with the infinite number of domain elements? You're welcome to use the textbook way or my you know idea of calling this kind of infinite domain. For me, I call it use the method of arbitrary elements. Okay, so here use the method of choosing arbitrary elements. And from the textbook, by the way, it's method of, it's too long, generalizing from generic particular. Okay. So in case when you're studying this with the textbook problems, I'm giving you 2 names so that you're not confused. What do they mean by method of generalizing from generic particular? This method is very useful, everyone, because basically what you do is this. Here's an example. Suppose I have, X, Y, Z. There are so many elements in the domain, and dot dot dot. There are infinite many elements, and let's call this set to be the set of even integers. I'm just making up, okay? Making it up. This is a set of even integers, everyone. Now, cover your eyes, and suppose you picked a random element in the box. Say X. Say choose X and Y. So say you chose X and put it here. You chose Y and put it there. X is equal to, Y is equal to. Everyone, because X and Y belong to the set of even integers, what kind of generic DNA does X have? X can be written as, because it's even, X can be written as what? From my first slide above. Thank you, Carol. Definitely. You chose X in the set of even integers. That means X must have this kind of DNA, 2 times by K. And K is some, chosen integer. So some integer K in Z, okay? How about Y? You picked a Y from set of integers, and Y also has the similar DNA. Can anyone tell me what would be the expression of Y? If you're wrong, that's okay. Just be confident. X is 2K, and Y is also belong to the set of even integers. Carol, first thing I want to tell you is that this Y belongs to what? Y belongs to the set of even integers. Do you agree? Set of even integers. So having 2K plus 1, it's not possible at the moment because we're not having an odd integer here. Daria, did you? Okay. Did you mean this, Daria? Y equal to 2K? Okay, very, very good. 99% correct. 99% correct means 1% wrong. Does anyone have an idea what's wrong with this so far? You know, okay, yeah. This is a collection of even integers. Okay, collection of even integers. Everyone, I'm very happy that I brought this up right now because it's actually common mistakes from the students. Writing the same variable at the same time for both x and y, that means what? That means we're assuming x and y are equal, right? But we picked two different elements. We picked two different elements in the domain. So we cannot use the same variable anymore. We have to use two. If we use 2k at the beginning, we have to use 2 times by something else, say w. Thank you, Daria. 2w for y, where w belongs to the z set of integers. To me, I personally like K, L, and so on, in alphabetical order. But honestly, these variables are dummy variables, so don't worry about it. And then using these 2K and 2W, you guys go ahead and then prove that there's, prove that the predicate is true using X and Y. That's what we're going to do next. Before I do the proof, do you guys want a little break, 5 minutes? First comment, first serve. Or do you want to finish the proof and take some break? Or no? Finish the proof, okay? Okay, everyone, let's finish. Okay, looks like you guys are not too bored. You guys are not too, sleepy. So let's finish the proof. Tell me quick yes or no. Do you understand my method of arbitrary elements? Like picking some random number here with the DNA 2K, picking some random integer here, picking and then saying that 2W or 2L, whatever you want to call it. Do you understand 100% so far? Or near to 100? Okay. If you understood this idea, then you're ready to prove the following example. Let it begin. Okay, the question is this. Prove that the sum of any Okay, I'm going to highlight the word any because any two means it's a good indication of using universal statement. And proving universal statement, either two methods, method of exhaustion or method of arbitrary elements. Okay, so let me first change this to formal language. So formally quantified statements looks like this. For all two even integers say x comma y, for all x comma y in z, for all x, y in z, if both of them are even, x and y are even, if x and y are even, then what is our conclusion? The conclusion is this: the sum of the two even integers, x plus y, must be even as well. Do you know what it means? It means our conclusion is this: x plus y is also even. There you go. This is my formal statement. Okay, now that you know the formal statement is a universal statement, because it's a universal statement, we have to do arbitrary method. Suppose you pick some random, okay, you pick some random x and y with the DNA even. So here's the proof. Suppose x and y are arbitrarily chosen. Arbitrarily, I can't pronounce so well. Arbitrarily chosen even integers. Even integers, okay. And this, do you want to follow my personal habit? My personal habit when I try to prove is that I try to write down what I want to accomplish from. In other words, what's my goal? My goal is to show that sum of two even integers is even. So in blue, this is just my personal preference. Goal to remind me our goal is to show, we must show that the sum of two even integers, x plus y is even. So there you go. Now, look, since x and y are even integers, we have this kind of DNA. Oops. Since x and y are even integers, we can write them as the following. X can be written as 2 times by some integer, 2k, and then y can be written as 2 times by L. I'm going to use L. And please remember, k and L, they must be different. You cannot write same k, where k and L are some integers. So write it down. For some k, okay, for some integers k and L. This is my setup so far. Okay, and then look at my goal. My goal must show that x plus y is even. So what you have to do is you have to add x and y together. It becomes 2k plus 2l, right? 2k plus 2l. So now x plus y is equal to 2k plus 2l, which works out to be 2 times bracket k plus l, like so. Wait a minute. K plus L is just some integer, right? And 2 times by that some integer is an even integer. Do you agree? Since K plus L is an integer, okay, it follows that the sum x plus y is also even integer. And this completes the proof. And I call it, this is pretty easy level because this is the first example. I want to give you easy example, and then maybe harder one later. Um, everyone, this kind of proof is called direct proof. Do you know why it's called direct proof? It's because, look at this. We assume x, y are even. So we call this kind of proof direct proof because we assume the hypothesis and get the conclusion, like modus ponens argument, and get the conclusion. So if you directly assume the hypothesis to get the conclusion directly, then this kind of proof is called direct proof. Sometimes we use contrapositive later on. Sometimes we use contradiction proof, but that's for week 3-3 video. So here you go. This is called direct proof, kind of using modus ponens argument form. Okay. All right, everyone. I think we can take some break for 5 minutes and come back at 1:12. 1:12. Okay. Thank you and see you soon. Okay. Is everyone here? If you guys are ready, then we can continue talk about the same example here. Sum of two even integers is even, but I want to mention something about common mistakes from the students. Okay, thank you, Daria. Okay, hope everyone's ready. And this will show up in the midterm because it has been in the 2019 winter. Well, not because of that, it's just a usual exam type question. The common mistakes from people. Some people, when they prove a statement, they use examples. For example, look, when you want to prove the statement, hey, the sum of any two even integers is even. Okay, I know one of them. Say 4 plus 6 is 10. Okay, I'm done. So the common mistake is, say they try this way, x equal to 4, and say x equal to 6. And hey, G1, x equal to 4 and x equal to 6, their sum is x plus y is equal to 10. I've done the proof. Do you think this is a correct proof or incorrect? Of course, it's incorrect because I just said it's common mistakes. But remember, proof by example doesn't exist. Of course, you're welcome to check the example to make a conjecture. Conjecture means you can use the example many times, and you can predict what's going to happen as the truth value. But you can only predict using an example, like Riemann hypothesis. It's not proven yet. Another mistake is that suppose they knew that we have to use the generic element, the arbitrary element with the DNA 2k. X is equal to 2k, and y is equal to also even integer, so they wrote 2k. And you guys know that writing the same variable k and k, it's not wrong. It's not good because here's my comment. We cannot assume x and y are the same. Look, if you assume x is equal to 2k, y is equal to 2k, then you're assuming x and y are the same element. But that's not the case, right? We usually pick up two different numbers, right? For this example. And another, common mistake is that skipping steps. For example, we instead of people skipping this first step and second step, and only wrote, okay, x plus y equal to 2k plus 2l, which is this. I understand your intention that x is 2k, y is 2l, so it works out that way. But do you agree with me that we need to define what x is, what y is, and what k is, what l is? Do you understand? So we need to define what they are in order to use them. So skipping steps, or maybe even skipping this step to get this one. So that's jumping to a conclusion part, which is another common mistake. And I see quite often this assuming conclusion from the students as well. Assuming conclusion is like this. I'm also going to use the same example here. Suppose x and y are even integers. Suppose x and y are even. Okay, students started very well. However, assuming conclusion is another common mistake because some people write this way: if x plus y is even, then I get, x is equal to 2k, y is equal to 2k, and so on. Everyone, assuming the conclusion x plus y is even, it's not the right approach because we want to prove x plus y is even. We don't want to assume our truthness of the conclusion at the beginning. Do you understand? So that's the another common mistake. So please don't assume the conclusion. Instead, assume the hypothesis here. X, Y are even. Okay. Then you can use the direct proof, continue to prove, to show the conclusion X, Y is even. Did I make things a little bit clear about the common mistakes, everyone? Do you have any questions? I know it takes a little time at the beginning. It takes a time to write it like this. But that's the whole point. The whole point of the course, this course, is that we want to write it formally, and we want to prove it clearly. So that's one of the important requirement for the course at the end. Okay. Right. So we just finished proving universal statement both ways. Method of exhaustion, and another one is method of arbitrary elements. Proving universal statement is exactly the same as disproving existential statement. So disproving an existential statement. This is exactly equivalent to proving universal statement. Let it begin. Here's the question. This question talks about prime number and composite number as well. And you guys know the definition of prime numbers. It looks like this. In case you guys forget about it, I'm going to write down prime number definition. Prime number definition is this. For all pair of numbers Rs in the set of positive integers, if we can write down n equal to r times by s, and then do you remember? We had only two cases. Then either this case or this case. Hopefully you guys can tell me one of the answer, okay? R equal to what and S is equal to what? Okay, so one of the possibility is that R equal to 1 and S is equal to N. R equal to 1 and S is equal to N, or R equal to N and S is equal to 1. So only the two possibility when we talk about prime numbers, right? How about composite? When we say a number is composite, then we say there exists a pair of numbers R, S in Z plus such that such that if you can write n equal to rs, and the pair of numbers r and s must be in between 1 and the n itself. So like this. You have two cases. Mm, actually, not two cases. You have to have this case. What r is greater than 1, less than n, and s is greater than 1, less than n. So this is the definition of a composite number. Okay, long story short, everyone, as soon as you have this kind of condition, r is greater than 1, less than n, s is greater than 1, less than n, right away that number is called a composite number. Oh, Ayanfe has a question. Could you scroll up a bit? Up to here, or Ayanfe, up to here, or a little bit more above? Okay, okay, you're welcome. All right, everyone, we have prime number and composite number and definitions. Hopefully, we can use these definitions soon. Okay, just keep that in mind. For now, let's go ahead and disprove the following statement. Show that, show that the following is false. There exists n in z plus such that this number n squared plus 3n plus 2 is prime. We want to disprove this by using the negation of this statement. So let's write down the negation. Negation of this statement is for all n in z plus, for all n in z plus, the negation of this n squared plus 3n plus 2 is not prime. Is not prime. Okay. Now you see we have a universal statement, n in z plus. What kind of method should we use? Method of exhaustion or method of arbitrary elements? Could you tell me? It's one or the other. Should I use method of exhaustion or method of arbitrary elements for this one? Okay, thank you, Carol. We have to use arbitrary elements method because you cannot check every single integer n, like 1, 2, 3, 4, 5. You cannot check every single integer n to prove the statement. So let's go ahead and use arbitrary element. So in the box, Mic test, can you hear me? Okay, good. Thank you. Okay. Yep, my wireless microphone battery, consumes a lot of battery, so I had to change that. Now it's working. I forgot what I said. Did I mention? Okay, I mentioned about this n squared plus 3n plus 2. Okay. Everyone, our goal is to show that n squared plus 3n plus 2 is not prime. In order to show that this is not prime, we need to show that this is a composite number. Do you agree? It must be a composite number. Then, look, one way or the other, okay? Don't you have a feeling? Don't you have a feeling that this number, n squared plus 3n plus 2, must be written as something like r times by something s in order to prove that it is composite? Don't you have a feeling that n squared plus 3n plus 2 must be written as a factor form? Factor form means something times by something. If I write something times by something, then I might be able to prove that that something factor must be greater than 1, so that we can prove that this number is not prime. Okay, here's the proof goes. Consider n squared plus 3n plus 2 in factor form. Okay, sorry. N squared plus 3n plus 2 in factor form, like this. Right, Daria, thank you. N squared plus 3n plus 2 can be written as n plus 1 times n plus 2. I know that everyone agrees up to here, this at least this factorization level. Now, tell me, do you think n plus 1 is equal to 1 or more than 1? Here, n is chosen to be set of positive integers, right? Z plus. So the minimum number n you can have, the minimum n you can think of is 1. 1 plus 1 is 2, which means greater than 1 or more than 1. Thank you, Kira. And look at this. This is even worse. N plus 2 is 3. I mean, the minimum number it can have is 3, which is greater than 1. Okay. As soon as you see it's greater than 1, what is our conclusion for n or about this number? The conclusion about this number is that n squared plus 3n plus 2 must be a composite number. Note, so both factors, n plus 1 and n plus 2 are greater than 1, Therefore, okay. Therefore, here's my conclusion. The conclusion is that n squared plus 3n plus 2 must be a composite number. Whenever you hear the word composite, it's a negation of prime number. So it's not so it means, i.e., n squared plus 3n plus 2 is not prime. And this completes the proof of disproving that existential statement about n squared plus 3n plus 2 being prime number. Okay. Thank you, everyone. This is the end of part 1 video of today's lesson. Part 2 will be more fun and more shorter, and it's about rational numbers. Before I proceed to part 2, any questions so far? Are you guys following me okay with the last example? If you have questions, feel free to ask me. Okay. Um, you can take a screenshot. You can watch this again, maybe after a couple hours from the last video or this video or the lecture. Whatever you wanna makes you work. Okay. Okay. Whatever works for you. All right. Next, we're gonna do direct proof and counterexample part number. Still, it's one actually. Still, it's one in overall video, but we're talking about rational numbers. Okay, since this is going to be very easy, I'm gonna do really quick. Yes, it's a fraction. It's a rational number. Why? Because the numerator is integer, and then the denominator is also integer. Okay, the denominator is also integer, but the denominator cannot be zero. But denominator cannot be zero. That's why. Now the second part is 7 a rational number? It's an integer, which is integers are subset of rational number. Yes. 7 over 1. You can write 7 as a 7 over 1. And this 7 over 1 is indeed a fraction, integer at the top, integer at the bottom. Integer at the top, and then integer at the bottom. But the bottom cannot be 0. Do you agree? It cannot be 0. That means you guys know the answer. Obviously, 2 over 0 is a rational number. Yes. Am I wrong? Okay. Okay, you guys know that I'm joking. 2 over 0 is no, it's not a rational number because the denominator you cannot have can't be 0. Okay? At the denominator, it should be non-zero number, non-zero integer. Okay, do you think this decimal number 0.1212 repeated a rational number? Yes or no? This time, okay. You guys knew that I will ask this question, eh? It's yes. But why? Why is this ugly decimal number is a rational number? Can this decimal number be written as a fraction? Yes, bar means repeating. Yes, repeating means even though it's non-terminating decimal digits, as long as it's repeating, then it's a rational number. That's how we learn in high school, right? But more precisely, we call this number as a rational number because 0.121 to repeat it can be written as a fraction, like Carol said. 12 divided by 99, which is the same as Carol's answer, 4 over 33. It's integer, and it's integer at the bottom, but it cannot be equal to 0. Sorry, it does not equal to 0. It's already not equal to 0. So there you go, everyone. As long as the top is integer, bottom is integer, non-zero integer, then surely it's a rational number. Okay, let's move on to the next page. Here's the proper meaning of that rational number. If you can find means existential statement. If you can find A and B such that the top is integer, some integer A, Hello, mic test. Is it working, everyone? Okay, good. Okay. Yeah, I have two devices, microphone, wireless microphone, and receiver that connects to my computer. This time the receiver battery went out. Sorry about that, everyone. Okay. The answer is yes. It's a rational number because m is an integer, n is an integer. So sum of the two integers become integer. And look, everyone, the bottom part, m times by n, is also integer. But we need to be a little bit careful. Do you guys 100% agree with me that m times n is going to be non-zero? Non-zero number? Yes or no? Okay, good job. Yes. M actually m and n are non-zero numbers. Both m and n both are non-zero numbers, so that non-zero number multiplied by another non-zero number becomes another non-zero number. So here you go. I'm gonna write that down clearly. M is non-zero number, and okay, I'm just gonna use this, and n is non-zero number. Therefore, m times by n is non-zero number. Okay, hopefully, okay, this is makes sense because it's actually not hard to understand, but something to remind ourselves. It's very important that we need m not equal to 0, n not equal to 0 to make mn not equal to 0. Um, you guys know from before, this kind of property is called a zero product, uh, zero product property. And I'm going to explain what that is actually. Here you go. If the zero product property says if neither of two numbers, say m not equal to 0, m not equal to 0, n not equal to 0, if both of them are non-zero, then their product is also not 0. So m times by n is not going to be 0. That's what it means by zero product property. And we might need this in order to prove the following statement. Okay, here's the question. For you, I have a question for you. This is the last one for today. Prove that the sum of any two rational numbers is rational. Do you think this statement is a universal statement or existential statement? What do you think? The statement prove that the sum of any, okay, I'm gonna stop here, any two rational numbers is rational. Whenever you hear the word any instead of some, then it's a good indication of a universal statement. Right, Carol? It's a universal statement. So let me change this statement into a formal language here. For all R and S. See, any two rational numbers means for all two numbers R, S belong to the set of rational numbers Q. Rational numbers Q. Okay. Their sum R plus S is rational. R plus S is irrational. In this case, I didn't use if-then statement. Do you know why? It's because I'm already specifying the condition here, R as being rational already. So I just have to check the function is rational. You know, when you use Java or other code, is, you know, is blank or is empty, you know, is rational. So that's the function, right? So we just have one predicate, which means is R plus S in Q. That's what it means. Okay, so once we're done with the universal statement, now you know what to do. It's a universal with the method of arbitrary elements, because our domain is infinite. Rational numbers, we have infinite number of elements to check. So proof. Let's pick some generic element R and S from Q, which is rational numbers. Suppose R and S are arbitrarily element, okay, rational numbers in the domain. Okay, and what is our goal, everyone? The goal, my goal here is to show, we show that R plus S also belongs to Q. Like this. That's our goal. Okay. I'm gonna write R here. Everyone, we have R here. We have S here in Q. In the set of Q, we have R and S. Suppose you guys pick R from Q. It has this kind of DNA because it's a rational number. R can be written as some fraction A over B. Since both R and S are rational, okay, R can be written as A over B. R is equal to A over B, where A, B are some integers. A, B belongs to some integers. And what is another condition that we need to add? And can you have denominator 0? Obviously, the denominator cannot be 0. So another restriction that we must have is that B cannot be 0. So where A, B are integers, B cannot be 0. That's our R. And S is equal to A over B, where A, B is in Z and B is not equal to 0. Okay. Everyone, am I correct so far, or are there any errors from my proof? Is there an error in my proof so far? Okay, Veronica, Kira, both of you are perfectly correct. I am wrong at the moment because I'm assuming R and S are the same thing. In other words, A and B, variables are recycled here. I need to use two different letters, say C over D. C over D, okay? Because we pick two different numbers from the set where C, D belongs to the set of Z and our D is not equal to 0. We must have that condition. Otherwise, it's not a fraction or it's not a rational number. Okay, now we want to show R plus S. So now we do summation of R and S. R plus S is equal to A over B plus, what is that? C over D, like so, equals. Okay, can I skip some steps and tell you the answer for this summation with a common denominator? The common denominator becomes BD. So the numerator becomes AD plus BC over the common denominator of BD, like this. And you guys know that AD are some integers, BC are some integers. So AD plus BC is just an integer. Integer. And BD is also an integer. But BD cannot be 0, everyone. BD cannot be 0 by the zero product property. If both M and N are non-zero numbers, their product must not be 0 either. So that's why we have BD to be not 0. Now, since AD plus BC and BD not equal to 0, actually, no, I don't want to confuse anyone. AD plus BC and BD are integers. And BD is not equal to 0 by the zero product property. Everyone, it follows that R plus S is indeed a fraction. R plus S is indeed a fraction AD plus BC over BD, which means in Q. Congratulations, everyone. This is what we wanted to prove. Like so. Okay, here's my plan, everyone. My plan is to give you the list of proofs you should know. List of proofs you should know for the midterm. For the midterm, maybe some numbers might be changed. For example, instead of M plus N over Mn, it could be C plus D over EF. Those things, little changes may occur. But if you study the proofs that I'm giving to you for the midterm, you'll be well prepared for the midterm part of the exam, which is last 2 questions probably. Yeah. So yeah, I'm gonna give it to you the list soon, and then practice midterm published soon, and this video as well as this week 3 video soon. A little bit too much work for me at the moment. If you can wait for me for maybe until tonight, then most of the contents will be uploaded. Okay, thank you very much, everyone. This is the end of today's lecture. If you have any questions, I'll still stay here until everyone left. Okay, until 2:30. Thank you, and have a great day. You're welcome. You're welcome, everyone.